Hello, welcome to this new lecture of the course Transportation Network Analysis. In the last class, we were discussing about user equilibrium, the equivalency conditions, and how the solution obtained is unique. So, today we'll be starting a new discussion on system optimization formulation. So, this is also a type of traffic assignment. So, until now, we have only discussed about user equilibrium as a traffic assignment problem. This is another class of traffic assignment. So the objective function in Bachmann's transformation is a mathematical construct. So that's why we are considering another optimization formulation. So we have discussed this that the Bachmann's transformation, which is the optimization formulation for user equilibrium, does not have any intuitive objective function. Okay, so it is just a mathematical construct. But in system optimization, the objective function is straightforward, and the constraints are the same as Bachmann's transformation. Okay, so the objective function in system optimization formulation is the total time that is spent in the network. Okay. Now this total travel time spent in the network is a measure of the network performance. Okay, you can think of it as it is kind of somehow connecting it with um, the congestion characteristics and so on. So let us look at the optimization formulation of system optimization. So here we have zx tilde x here, and we are representing not by zx because we want to differentiate it with the objective function of the user equilibrium. So here this is the sum of xa times ta over all the links A. Okay, so this is the expression for the total travel time spent in the network. Okay, and to get an intuition behind this, for example, if in the network there is a single link, okay, now how will we represent the total time that is traveled by different people that is traveling on that link? So everyone will be experiencing the travel time of taxa, right? And since there are xa number of people on that link A, so therefore the total travel time that is experienced by the people traveling on that link is xa times txa. And if there are multiple such links in the network, then we need to sum this over all the links A. Okay. Now the constraints are the same as the user equilibrium constraints, that the sum of the flows on all the paths connecting R to S is equal to the travel demand, and the path flows are non-negative, and the link flow is related to the path flows by this equation here. Okay, so the constraints are the same as before, so we are not discussing them here. So this shown optimization program is called system optimization program, okay, or SO in short. So note that the solution from this program need not represent an equilibrium solution. Okay, so the solution of this need not be the same as the solution of the user equilibrium problem. And why is that? Because in system optimization, it involves joint act of travelers to minimize the total system travel time rather than their own. Okay, so in the user equilibrium, we have this assumption that all the travelers are minimizing their own travel time, but this need not be the case in the system optimization solution. So in system optimization solution, everyone is following that way of traveling, so that the total system, that is total travel time that is spent on the network, is minimized. Okay, so while doing that, it might happen that some of the travelers might have to travel longer than the shortest travel time that is possible. Okay, so that's why this solution need not be the same as the user equilibrium solution. So this is saying the same thing, that at SO flow pattern, some travelers may be able to decrease their travel times by unilaterally changing routes. Okay, therefore SO is not a stable situation and is less realistic than user equilibrium. So since some of the travelers can be able to decrease their travel time by unilaterally changing routes. So that's why it is not a stable situation as the equilibrium case, and that's why it is also less realistic, because in the reality everyone will try to minimize their own travel time only. So then the question becomes, why are we studying the system optimization formulation? The reason being is that this objective function of system optimization, that is the total system travel time, serves as a yardstick for network performance. Okay, so this kind of tells that the best solution one can get so that the total system travel time is minimized is the one that is obtained by system optimization. Now, if the actual flow pattern takes place based on the user equilibrium solution, then we can get an idea that in that case what is the total system travel time, and then how large is that total system travel time as compared to the one that is obtained in the system optimization. Because in the system optimization formulation you will get the least possible total system travel time. Okay, and the one obtained from user equilibrium, the total system travel time can only be the same or higher than the one obtained from system optimization formulation. Okay, so that's why it serves as a yardstick for network performance. Okay, so that if everyone is behaving selfishly as in user equilibrium, so how much total system travel time increases as compared to the best that is possible, that is the one in system optimization. Okay, so that is what is of importance to the travel management authorities. Okay, so this is saying the same thing, the solution of SO provides the minimum possible total travel time. Okay, so let us define this marginal travel time of link A. So this is equal to the travel time on link A plus xa times derivative of this travel time function with respect to xa. Okay, so what does this mean here? So this function marginal travel time of link A can be interpreted as the marginal contribution of an additional traveler, for example an addition infinitesimal flow unit on link A to the total travel time on this link. Okay, so let us try to understand it further because it seems a slightly involved concept. So it is saying the marginal contribution of an additional traveler on link A to the total travel time on this link. So it will have two components. First is the travel time Txa, which is the travel time that will be experienced by that additional traveler when the total link flow is xa. So if we add a very small flow to a link A that is carrying xa, so then since it's a very small flow that is getting added, the travel time will stay the same. But for this small flow, the travel time that will be experienced will be Txa, right? And to the flow that was already existing before, the additional travel time burden will be this given by dTA by dxa. This is the rate at which the travel time increases if you change flow. Okay, so this is the additional travel time burden that this traveler inflicts on each of the travelers already using link A. Okay, and since there are xa of them, so that is why we have multiplied xa by dt by dxa. Okay, so all of this discussion that we have been doing in the traffic assignment discussion, starting from user equilibrium, then we digress towards optimization, unconstrained optimization, constrained optimization in continuous case, and KKT conditions, and then we are now discussing about system optimization. So all of this is being followed from this reference called Urban Transportation Networks by Yosef Shafi. So that is a very good reference. So one can also refer to that for additional examples and assignments. So before we can define and understand this system optimization formulation further, let us represent the marginal total travel time on path K connecting OD pair RS by CKRS tilde. Okay. So therefore, the first order conditions for SO program are as follows. Now we are not deriving these first order conditions for SO program, but the derivation follows in the same way as it kind of follows for the first order condition of user equilibrium. So both of these formulations for user equilibrium and system optimization are the ones that have non-negativity constraints and linear equality constraints. Okay, and therefore the KKT conditions can be derived in a similar manner as we have seen before. Okay, so this derivation is available in Sheffy's book, but because of the constraints of time, we are not discussing them here. But we will just directly state what are the first order conditions for system optimization program. So these are the conditions. Now these two constraints are the same as before. Okay, that is the sum of the flows on all the paths connecting R to S should be equal to the demand from R to S, and then the path flow should be non-negative. Now these are the new conditions that we have, but these are also not looking entirely new, because these look very similar to the ones we had seen for the first order conditions of user equilibrium formulation. Okay, just the only difference that now is that instead of CKRS, that is the travel time in path K connecting R to S, has been replaced by this C tilde KRS. So that is the marginal travel time on path K connecting R to S. Okay, and instead of this URS, we have U tilde RS. Okay, so these conditions 3 and 4 are the same as the flow conservation and the non-negativity constraint. So there is nothing surprising here. So let us consider these two conditions here, the first two ones. So what it is saying is that, again, here we can divide the paths that are connecting R to S into two types. One which have positive flow. So if FKR is positive, that is for a given OD pair RS, if the path connecting to that kth path connecting R to S has positive flow, then from this first equation what we will be getting, that C tilde RSK is equal to U tilde RS. Okay, and if we have a path K connecting R to S that is not getting used, that is it is unused, that is it is having zero flow, so then we do not get any additional information from this first equation. I mean, there is no restriction from there, and the only thing that we know is that the C tilde KRS has to be greater than or equal to U tilde RS from the second condition here. Okay, now considering that this U tilde RS is then has to be the least marginal travel time on any path connecting R to S. So therefore, what we can say is that for each OD pair at system optimization, the marginal travel time on all the used paths is equal to this and is less than or equal to the marginal travel time on any unused path. Okay, so these are the used paths. So the marginal travel time on all the used paths is equal to the minimum travel time on any path connecting R to S, and this is less than or equal to the marginal travel time on any unused path, this one. Okay, so you can see that this definition is almost the same as the definition of user equilibrium, just that instead of travel times you have replaced by marginal travel times. Okay, so then you can get the idea that if the link travel times over the network are replaced with the marginal link travel time Txa, so if you replace for every link A, instead of Txa you write T tilde Axa. So we have seen what is the expression for this T tilde Xa. So this is equal to Ta plus Xa times the derivative of dTA by Xa, right. So once the travel time function of link A is given, then we can determine what is this T tilde Xa by using this expression here. Okay, so now if we replace the travel time of every link with the marginal travel time function, and on that new network if we suppose determine the solution of the user equilibrium, then that solution which is obtained is actually the system optimization solution for the original network. Okay. So this is very important. So this is telling that you can obtain the solution of system optimization by solving a modified user equilibrium problem. And in that modified user equilibrium problem, you have to replace the original travel time functions for every link by the marginal travel time. Okay, and then solve the user equilibrium problem, that is determine the equivalency conditions and then find the solution, and that solution will actually be the solution of system optimization. So this is very interesting. Now let us consider an example to show the difference in solving the same problem with marginal travel times versus travel times. Okay, so we had, when we had started to discuss about this system optimization, so then we had seen that the solution of system optimization need not be the same as the equilibrium solution, that is the user equilibrium solutions. Okay, there can be very special cases where both of these might offer the same solution. For example, when suppose the flow on the links is very small. Okay, so if that is the case, then the travel time function, for example, we usually look at the travel time functions like this. So if the flow is very less, say in this region around, so then the travel time is hardly changing with the flow. So then we can say that TAXA is like a constant, just TA. Okay, so when you do that, then whether you solve the system optimization formulation or the user equilibrium formulation, they will give the same solution. Why is that? Because what is the objective function in the user equilibrium formulation? It is summation is TA omega dw, where the summation is over all the links and the integral is going from 0 to xa. Okay, so this expression will come out to be equal to summation xa times TA over all the links when the travel times on all the links are constants, and this is what the objective function of system optimization is. Okay, so in very special cases, it can happen that the solution of user equilibrium can be the same as the solution of the system optimization, but in the all the other cases when that is not the case, the solutions can be very different. Okay, so that's why solving the same problem, that is solving the user equilibrium problem with the putting the travel times, and then we will be getting the solution of the user equilibrium problem, and versus solving the user equilibrium problem but replacing the travel times with the marginal travel times to get the solution of the original system optimization formulation, these two things can be very different. Okay, so let us see an example to understand that. So we have this very small network here from one origin to destination, and there are two links. One is this link 1 and the other is this link 2. Okay, and these are the travel time functions that are given. So for the first travel time link here, this first link, this travel time function is varying like this very slowly, whereas for the second link it is increasing very fast here. Okay, so here suppose that the total flow from O to D is equal to Q. Okay, so you can see that this Q is such that this T2Q is less than T10, that is, even if all the flow takes place through the second link, the travel time that will be experienced on this link will be less than the free flow travel time that is experienced on the first link. So that is why all the flow is taking place on the second link only. Okay, so this is what it is saying. If the total OD flow is Q, the user equilibrium solution will be the one shown in the figure with x1 equal to 0 and x2 equal to Q. Okay. Now in this case, suppose Q is such that T2Q is less than T10, that is, this value is less than this. So that is why it is best that every user takes this second path only in the user equilibrium case. Okay, so then no one will choose this first path. Let us suppose that this first path is representing a freeway, okay, and this second path is representing a city street here. But the derivative of this second travel time function at x equal to q, that is dt2 dx2, seems to be relatively large here, okay, this slope, whereas there is hardly any slope here and this is 0, okay. So therefore it is possible that the marginal travel time of the first function here can be less than the marginal travel time of the second link here, okay. So what is the marginal travel time of the first link? So this is equal to t10 plus the flow through link 1 times the derivative of the first link with respect to x1, okay. Now since there is 0 flow here and this actually the slope is also around almost 0 only, so this is just equal to t10, okay. However, for the second link, what is the marginal travel time? This is equal to t2q plus q times of d t2 by dx2, okay, at this flow q. Now q is positive and this slope is also something positive here, seems quite large here, okay. So it can happen that although t2q is less than t10, but when we add this term also to t2q, it can be bigger than t10, okay. Now we know that in the system optimization case, the solution will be such that all the use paths will have marginal travel times to be equal and less than or equal to the marginal travel times on the unused paths, okay. So therefore, since we have t1q to be greater than t2 tilde q to be greater than t1 tilde 0 here, so this solution is not optimal from the system perspective, because it is possible that if some flow shifts from this second link to the first link, it might be possible that the marginal travel times of these two links become equal, okay, and in that case the system optimal solution will be reached, okay. So the system optimization solution to this problem may include some flow using the top route out as well, okay. That is, if one driver shifts from route 2 to route 1, his or her own travel time will increase, that is the driver will experience t10 instead of t2q. So in this system optimization solution, as I mentioned, that it may be that some of the travelers may not be taking their best choice, okay. So some might have to sacrifice their travel time in order to make sure that the overall travel time of the system is minimized. So in order to move from this user equilibrium solution where all the flow is taking place through link 2 only, and if you have to reach the system optimization solution, it might be better that some flow shifts from the second path to the first path, okay. Now when that happens, the flow that shifts to the first path, they will experience higher travel time because t10 is higher than t2q, right. But note that the travel time that is experienced by each of the remaining drivers on route 2 will decrease, okay, because since the flow on the second link has reduced now, so therefore this decrease has happened by this rate d t2q by dx2, okay. And if it such so happens that an increase of this T1 0 minus T2 q, that is the increase of the travel time that is experienced by the flow that shifts from path 2 to path 1, if that is offsetted by the decrease of this travel time which is experienced, the decrease in the travel time that is experienced by the remaining travelers on route 2, which is q minus 1 times dtq by dx2. Now this is an approximate value because this kind of assumes that the slope kind of remains the same here, whether it is at q or q minus 1, but you can kind of guess that the rate at which the travel time decreases for the remaining drivers on route 2 is something like this, and this is multiplied by the flow that remains on the second route. Okay. So from the system perspective, an increase of this in the travel time of the flow that shifts from route 2 to route 1 may be more than the offsets by a decrease of this. Okay. And therefore, the system optimization flow will be reached when T1 x1 plus x1 times derivative of T1 is equal to T2 plus x2 times the derivative of travel time 2 with respect to x2. Okay. So the main point here is that in the user equilibrium solution, every traveler tries to minimize their own travel time, but in system optimization, it might be the case that some of the travelers might have to travel longer so that the overall travel time is minimized for the network. Okay. And that is what is happening here, is that one traveler has to shift from this to this here. But when he does that, when he shifts from the second path to the first path, it also does happen that the travel time also decreases for the remaining drivers on route 2. Okay. So even though there is some increase in the travel time of the first flow which is moving from second path to the first path, there is also a decrease of the travel time on the remaining flow on path 1. Okay. So that is why it can happen that with this change the overall travel time might decrease, and that is why it might be best that some flow shifts from path 2 to path 1. Okay. So we will be continuing this discussion of system optimization in the next class. Thank you.